All right, so I was going to do another couple elimination problems going to add to YouTube. This is an in-class example. The best examples are the ones she uses in class because she makes the assessments, not me. Okay, I'm going to go through this real quick. Elimination, I didn't get to as much as I wanted to in SI, as much as I should have. Okay, so I'm going to do this example. I'm going to do one more that looks a little bit different, just so we're a little bit more. We can look at other problems and be a little bit more adaptive tomorrow in the assessment if it doesn't look exactly like how we've been studying so far. I went ahead and I wrote out the full shape of hydrogen sulfate. This was presented to me as OH2. Okay, I went ahead and wrote the bonds. I just like expanding things out, not totally necessary we do it in this case. But it will help and show that where our negative charge here is our nucleophile. Okay, now, this is actually the second video I made. The first one, I made the mistake of, I saw a negative charge, I saw a positive charge, I thought they would be, no. Elimination. Elimination, think double bonds and think beta hydrogens. Don't be distracted by a big positive charge there. Think beta hydrogens. So, where are my beta hydrogens located? Okay, I see a positive charge here on my OH2. Notice that when OH2 leaves, I get rid of that positive charge, I'm going to make water. So I have identified a good leaving group off the start. Usually halides, but something with a positive charge like that, notice if we make it leave, that charge goes away. So that's going to be favorable. So I've identified a good leaving group there. Because I've identified a leaving group, I can go ahead and find my beta hydrogens. My options are on these positions. If this is symmetrical, we can use either one. Okay. I have my base here as my oxygen with a strong negative charge. Bases are proton acceptors. Okay, you can take that hydrogen there. Elimination, think double bonds. I'm going to make a double bond. Okay, carbon can't make 5 bonds, therefore my water is going to leave. I get rid of that positive charge on there. I'm left with an alkene. Okay, double bond we added right here. We eliminated hydrogens from this. Okay, and we get water. Notice we've eliminated charges. Section 7.8 goes into like what's the basis of chemical reactions? More stable charge in the products and greater bond energy. We have more stable charge. This is going to be favored. This is what drives chemical reactions. So, okay. So again, read the directions carefully. Originally, I wanted to do something like an acid-base proton transfer thing almost, but I didn't read the directions and said elimination. And when I read that, I think double bond, I think beta hydrogen. One more example that's somewhat a little bit different, but it's also elimination. All right, and it says up at the top, it says elimination. Okay, I have a carbocation here, a secondary carbocation. If you don't know what that means, watch the videos before, explain in detail on identifying that and stability related with it. I have a spectator ion here in potassium. We know we can just get rid of that and make this OH minus. Who has electrons and who wants them? Elimination, though, think double bonds and think beta hydrogens, okay? Sweet. So no, I have one pair here on oxygen that need to attack a beta hydrogen. So this is my initial carbon with the carbocation on it. Think of your carbocation as the functional group in this case, where my beta carbons are on either side of it, and I have a beta hydrogen here and beta hydrogen here. We are not symmetrical in this case, so we have a decision to make. Which one's going to be more stable? Okay. The most stable double bond you can make is one with 4 groups on it. The groups can be anything. The more conjugated, the more substituted you get a double bond, the more stable it is, and the more of it you're going to get in your product. Okay. The least stable would be, I guess, no substituents, no conjugation there. Yeah, and then this would be slightly more stable if we only have one group, and so on. So the more conjugated, the more substituted I can get that alkene, the more stable it is. Notice that if I were to use this beta hydrogen, and I had oxygen come in, attack beta hydrogen here, lone pair, beta hydrogen, I'm making a double bond, okay? Awesome. Now, my product would look like a di-substituted alkene, 2 groups on it, okay? All I did, I took this hydrogen here, now I've made water, I took that hydrogen away. Now this carbon's only making 3 bonds, but I'd established a double bond, and now they're both making their 4 bonds, fulfilling their octet, okay? So this is the product I make if I use the orange hydrogen. If I use the pink hydrogen, my product looks like this, a mono-substituted alkene, which is more stable, this one. I don't know the numbers on these, but I would expect this in solution something like 90%, 95%, and this one like 5 to 10%. This one's more stable. And yeah, okay, so the more substituents we can get on alkene, the more stable it is. Okay, elimination. Double bonds, beta hydrogens, you're gonna be good with that. I encourage you to watch the other videos, and even more so than that, the examples she used in classes. Just the last 2 class periods, Monday and Wednesday, the whiteboards on the readings, go through those, okay? Write down what the problem was before without all the arrows and answers, okay? And try it on your own and quiz yourself. That's, I think, the best way to study that. Watch the videos if you need help. Encourage you to do that. Hopefully this elimination video helped you. Good luck on the assessment tomorrow.